So next up we have Helge from PT Scientists, who will be talking about Julia for space science and Antidote for complexity.
Thanks for having me. All right, I start again. Thanks for having me. This is my second JuliaCon, and I'm glad to be here, and I'm glad that JuliaCon has finally come across the Atlantic. You can clap for that. So I want to talk to you about the fact that it's still difficult to go to space and about the reasons that have nothing to do with physics. And finally, how Julia can help. So I work for a Berlin-based new space company called PT Scientists, and our plan is to land on the moon, put 2 rovers there, and with them explore the Taurus-Littrow Valley, which is the landing site of Apollo 17. And all of that until the end of 2019. So, piece of cake. Basically, the only thing we have to do is we have to do it a whole lot faster and a whole lot cheaper than the traditional space companies and space agencies do it. And I'm confident that we can, because actually there is some precedent. And in hardware, this precedent is called Coopsets, or as the established players like to call them, space debris with an antenna. No, seriously. There are several teams, or a lot of teams around the world, who've shown that you can actually fly to space with off-the-shelf hardware, with cheap commercial components, and you can get useful science out of that. And I mean, it makes sense. For example, there's companies doing Earth observations with constellations of CubeSats. And if you have like a huge constellation of satellites, if one of them fails, it doesn't matter, because with the next batch, you will just replace them. If you have just one, well, then it needs to be very expensive and very reliable. So in hardware, there's been a shift, so we can use cheap hardware. So how is it on the software side? Because actually a space mission is to a large percentage software. So you have the onboard software running on the onboard computer. So for avionics and for payload handling, data handling on board. Then you have the mission control system on the ground, which actually commands the satellite. And for complex missions, you have also stuff like mission planning systems or spacecraft simulators, where you can test your environment end-to-end on the ground. So how are these software systems today? They are like this in complexity. Space shuttle scale of complexity. Huge budgets, huge time scales. And I can tell you, before I started working for PTS, I worked for a traditional aerospace company in the vicinity of the European space agencies. And those systems were just massive. And how does this work? So basically, you come up with a nice design. You say, okay, everything is going to be very clean and easy. It's going to be nicely designed. And then you split the project up over the whole of Europe. You have many people working on that. In the end, it turns out like this in reality. So what we need to build in terms of software systems for space missions, we do not want that. So we do not want space shuttles. And by the way, if you ever want to know how not to do requirements engineering and what feature creep is, read up on the development history of the space shuttle. It's fantastic. So it was meant to do everything and did a few things, and those it did very expensively. So what we need are systems like this. Simple, lean and mean, but also forward-thinking and trying new stuff. So the goal would be, in my opinion, to massively reduce complexity. Because, as Dijkstra says it, simplicity is prerequisite for reliability. So I would say if you want to go to space, your system should be simple. Otherwise, it cannot be reliable. Why is it not that way right now? I have another nice Dijkstra quote for that. Simplicity is a great virtue, but it requires hard work to achieve and education to appreciate it. And to make matters worse, complexity sells better. Emphasis mine. So what can we do to reduce complexity? First, we have to discuss what kind of complexity I'm talking about. So in the famous No Silver Bullet paper by Brooks, there is this distinction between existential complexity and accidental complexity. So existential complexity is the complexity inherent in the problem you're trying to solve. So the things we care about, or as we call them, rocket science. And there's also accidental complexity, so the things we do not care about at all, we do not want to care about, non-rocket science, complexity introduced by the tooling, the programming language, the environment, and I would also add by your organization, etc., etc. So we cannot do anything about existential complexity because that's the problem we want to solve. But we can actually do a lot of things about accidental complexity. And the devious thing about accidental complexity is that it becomes invisible to the expert. So if we look at this piece of code, disclaimer here, no programming languages were harmed in the preparation of this talk. If I say, in your opinion, bad things about your favorite programming language, we can debate that endlessly offline. But as I said, they were not harmed. They're fine. Okay, let's assume we're a beginner. We're trying to learn to program. I've put all the concepts you have to learn to put hello world on your screen in different colors. So in Julia, this is, okay, we have to know what a function call is, or we have to learn what a function call is, and we have to learn what a string literal is. So that's two concepts. Seems fine to me. So let's look at another programming language. Oh yeah, taste the rainbow. So we have to know what is public. What does that mean? What the hell is a class? Okay, then it has something to do with hello world. Then we have these funny symbols. Is this the same public as this? What the hell is a void? You're asking yourself if you're not a native speaker, and why is it static? Okay, this is a function call, so we know that already. Then we have to know what a string is exactly, more funny symbols. Okay, what do we do with that? Yeah, yet again, okay, dots. You see what I'm getting at. So this is 12 concepts you have to learn. So I remember quite clearly when I started with programming, my reaction to this was like, okay, I can handle it. And my reaction to that was more like, yikes, what the hell? Let's become a mechanical engineer. That's what I did. So if I talk about this in the context of my work, so I'm a mission analysis engineer. My task is to figure out how we can navigate our spacecraft to the moon in the most efficient manner possibly and without violating any constraints, so thermal constraints, so we get enough sun and not too much sun from the right direction. We stay in contact with the ground stations, etc., etc. So what I really care about in terms of existential complexity is optimizing the trajectory. What I do not care about is dependency management. Anyone has used Maven? Did you have fun? Thank you. Build systems. Anyone has used CMake? AutoTools? A shell script somebody in your company or your university wrote? Okay, you see what I'm getting at. Memory management, compiler flags, linkers, libraries, is it static, is it dynamic? I don't care about that. Class hierarchies is also not really what I care about, and even syntax can get in the way. I think we've heard it in a few talks already in the conference. If we can write Greek letters and such things, it's really, if you want to translate math into code, that's really useful. And if you don't have that, you start to miss it quite fast. So 2 years ago, I was at JuliaCon saying, okay, my kind of people, so Astro and Nemesis, they already found the perfect programming language, and it's called Fortran 77. Now, they see the error of their ways, and they decided to switch, so I can finally announce that it's C++. So, yes, ESA and NASA, they're rewriting most of their Fortran codes in C++ right now. What could possibly go wrong? So just to put some emphasis on this point, let's have a look at C++ in terms of complexity. When I show this to C++, like real hardcore C++ people, they don't get the joke. They say, I need all of those. Yep, that's about it. Okay, I think we all agree that we don't need all of those. Usually at this point in the talk, when I'm talking to non-Julians, when I'm not preaching to the choir, is I show this slide. So this has a bunch of micro benchmarks. It shows that Julia is basically in the same ballpark as C++ and Fortran. And yeah, how about no? Let's stop doing that. First, because I've milked that paper enough. And secondly, I think we do not have to talk anymore about if Julia is fast. It is, we won. But we have to talk about the how, and I think the how is even more important. And what I want to talk about now is how we can actually leverage the type system to introduce abstractions, to make our code more domain specific, to actually leverage that speed. So let's start with an example which is actually, it might seem trivial, but it has far-reaching consequences. So this is actually quite interesting. So if you look at any Julia code on GitHub, dealing somehow with the planets in our solar system, at one point in the Git history, you will find this. So there's a dictionary which contains other dictionaries with the constants for the planets. For example, the radius of Earth, which is fine as a first shot. But you're not telling the compiler anything about what you know about your domain. So this is just, for Julia, this is just a dict. So you might improve on that like this. Okay, so we now have a planet type which has a radius which is of type float 64, 46, sorry, I'm German, 64. And now you have the advantage you can have other fields with other types, so it's not a dict of symbol any anymore. And then you have an instance of planet which is Earth. But I actually think that you can go further than that, because right now every planet looks the same. There's also the case that you don't have the same kinds of data for every planet, so you would have to work with missing data, which is now possible in the newest version, or it used to be before, but it's better in my opinion. And so let's go one step further. So let's say we have an abstract type called planet. Now we say Earth is just an empty struct of type planet. And now we define the constant Earth to be the instance of this empty struct, so a singleton. And we are actually telling the compiler more about our domain with that, because now we know there's just one Earth. You cannot instantiate another Earth with different constants. And now we can also dispatch on Earth. So we can have the same constant as we had before. We say mean radius of Earth equals this. So how is this useful? Right now this looks more complicated than the version before. But actually, if you're thinking not about your own package, but you're thinking about an ecosystem, building infrastructure, this is actually more extensible. So let's say I want to have units with that. I don't have to go all in and say, okay, all my constants now are quantities from the unitful package. I can do something like this. I can say, okay, I define mean radius on float 64 on Earth. This gives me this. But if this type is a quantity from the unitful package, I want it in kilometers. And okay, I can still define a standard function for that, which gives me the the normal float 64 value. And by that, the system becomes extensible. So basically, what I want to say, in the words of Julia core developer Obi-Wan Kenobi, use the type system, Luke. Okay, let's have a look at the state of the ecosystem. So Julia for space science. 2 years ago, I presented my package astrodynamics.jl. And what I realized at that point is that I was building a lot of essential infrastructure, what you need for doing, in this case, astrodynamics, but also useful for other branches of space science. For example, time representation, state vectors, etc. And I had a brilliant idea. I thought, okay, astrodynamics.jl is going to be a meta package. I'm going to split it up and have separate packages for all these sub-packages which have developed over time. And the impact was this. Because I realized I am in fact not Chris Rackauckus. And instead of one unfinished package, I had like 15. But in the end, good things came out of it still, and even differential equations.jl was not built in a day. So as I said, I split my package and organized it in a GitHub organization called JuliaAstro Dynamics. And with that, I got the attention of the JuliaAstro guys, because they said, okay, there is in fact overlap in the stuff we do. So the decision was made to start building common infrastructure, to have common ground. And what I did was I moved 2 of my packages over, and these are astrotime.jl, which is a high-precision epoch type that supports all common astronomical timescales. And this might also be interesting to non-astronomers or non-astrophysicists because it supports leap seconds. And you can define your own timescales. And another package, and I think this is the most important one, which is called astrobase.jl, which is a work in progress. So it defines common types and interfaces for astro whatever packages and the basic constants and functions. And I think this is a point that was raised by other people in the conference already. So for example, by David Enthoff in his Queryverse talk, or by Andy Ferris, is that you have to have strong interfaces. By the way, if you haven't been in the meta-programming session by Andy Ferris yesterday, you really should take a look at the recording. It was basically a wolf in sheep's clothing. So everybody expected macros, but what we really did talk about was the type system. So honestly, it was a wolves in wolves' clothing, but you should do yourself the favor and check it out. Talking about interfaces, one example I want to give you. So right now there are several packages out there which provide ephemerals. So the position of the planets at some point in time. And what we are doing right now in Astrobase is defining interfaces for that. So that it doesn't matter if you're using JPL ephemeris, if you're using CalcF, that you can always expect the same interface. So if you want to get the position of the planet, you just have this one position function. You pass in some kind of ephemeris, you pass in an epoch, and you pass two celestial bodies, and you get the position of one body with respect to the other. And as I said before, the planet example seemed trivial, but it has repercussions here. So for example, since we can now dispatch on planets, we can do something like this. So if we are using a SPICE kernel, which is one kind of ephemeris, and the origin is Jupiter, and the target is one of Jupiter's satellites, we can dispatch to the correct ephemeris because we then use a different kernel. So if you take one thing home from this talk, is do care about your interfaces, and I think this is the basis for the great success of the successful Julia packages. For example, my favorite, differentialequations.jl, or the JUMP ecosystem and others, that they have strong interfaces. And we want to have that. So another good thing about the cooperation with JuliaAstro was that JuliaAstro is actually a part of Open Astronomy. So a kind of umbrella organization for different open source astrodynamics or astro whatever projects. And based on that, we had a great GSOC project this year. And our student Praka completed a boatload of pull requests, and I can say now that he was able to get rid of a binary dependency for AstroTime, which was really a great accomplishment. And with that, I want to have another small detour talking about the interoperability. So interoperability in Julia, the story is just fantastic. We can assimilate everything. So whether it's C, C++, Fortran, and this is really, really important, because if you start writing new stuff or start rewriting stuff in Julia, which is what we're doing a lot right now, validation is really easy, because you can just call out to the standard libraries like ERFA for astronomy or others, and you can validate your results in Julia. So I would say in that regard, Julia is a bit like the Borg in Star Trek, but more benevolent, less threatening. Okay, until March, this was the state of the art, but then an unlikely hero appeared. So on exactly, not March, May, I'm sorry, May 13, 2018, I hope I'm pronouncing that right, Honan released his package satellitetoolbox.jl. And this is really a fantastic project. He has worked on that starting in 2014 as part of his research for the Brazilian National Institute for Space Research. And he has implemented really a ton of features for early phase studies. So pre-phase A in space parlance is before you have real money. It's just to see if a mission is feasible. And he implemented so we have native Julia implementations of famous orbit propagators like SGB4, something I'm really excited about. Reference frame transformations, and a lot of functions dealing with the physical environment around Earth, so for Earth orbiting missions. And it's actually integrated into a nice Qt application, which they use at INPE for simulating these studies. So really a fantastic application of Julia. So what we did in the end, we again realized that there's a lot of overlap between JuliaAstro and satellite-toolbox.jl. So we decided to collaborate, to get together, and we rebranded as JuliaSpace. So watch this space in the future, pun only slightly intended, because there's a lot of great stuff coming up if you're interested in Julia as in space applications. And I think the potential is really limitless. I would go as far and say that for astrodynamics applications, there is no match for Julia right now. And finally, because many of the things I talked about were I kind of pulled an Elon Musk on you, because many of the things are not existing yet, but we're working on that. And I want to finish with a real Muskian pipe dream, one that Ronan and I share. How about having a CubeSat with avionics running in Julia? That would be great, wouldn't it? So, with that, please find me on GitHub and on Twitter, and I would thank you for your attention.
Thank you very much for your talk. Does anyone have any questions for Helge?
So what does it take to put Julia on those CubeSats in the avionics bits that you referred to? Is it some weird processors? I mean, I'm assuming some space hardened stuff.
Not much actually. Since the lifetime of many CubeSats is quite short, you can actually do with a Raspberry Pi, for example. And since Julia is already running on the Pi, that might be possible. What's more difficult, as I would say, is the operational environment. So keeping the process running, integrating it into the software infrastructure of whatever is running there. But since many CubeSats are quite hackish, that shouldn't be too difficult.
Would garbage collection be an issue?
That might be. But there was a paper some months ago that analyzed the needs for real-time or soft real-time in CubeSats, and many of those don't really have those requirements, so you could do with that. But if there was a way to control the garbage collection, which would enable more soft real-time-ish applications, that would be great in that regard.
Great talk. I like seeing where this stuff is going, and I've liked seeing where you guys have used to be asking for a lot of different things, right? With the second order ODE solvers and a lot of unitful support throughout the ecosystem. I'm kind of wondering what the JuliaSpace and JuliaAstro people are still looking for. Like, what are the parts of the Julia ecosystem that still need improvement for the types of research that you're doing?
That's a great question. From shooting from the hip, I would say manpower. But this is a problem that every open source project had. So from my taste, we do not need much in features. That's all there. What we needed, what we desperately needed, was stability. So 1.0 is actually the major mark where I can start pushing for real. And with the ODE solvers, for example, we're set. We can work with that.
I think Chris has solved ODE solvers forever for everyone.
Does
you get
anyone
an ODE solver, and you get an ODE solver.
Any more questions for the speaker? If not, we'd like to thank Helge again.